I think if you sit down, please, we can start. So you have seen a lot about Börje. So Börje is now living in Sweden for 70th year, right, Börje? How many? 70. But this is my 20th year, Börje. And when I came, it was exactly 1st July 1992. And for me, it was a very cultural shock when I see first time Börje. So they took me from the airport directly to Börje's home. And I saw Börje in a half pant and cleaning the home. And then I asked these two PhD students who brings me here. One is here, I think Per Söderlind was, and other was Joachim Trigg. I said, why a professor has to clean? Because in India, you get a servant to clean. And so I have a very hard time with Börje when he comes to the office and he sits on the floor and I have to sit on the chair. And third thing was I cannot take his name Börje, so it was very difficult time for me in the beginning to deal with Börje. And then he always come in the middle of night. As Ulf already mentioned, and that time they have a meeting on NFR, and 12 o'clock he asked me, Rajiv, can you make a coffee? We have a committee meeting. I said, will I get some money or support? He said, yes, yes. But I never get a support, but I make a coffee. So you know that Börje has a very long list of publications. I don't want to show his long list of publications. So I just show his top 3 cited paper. So you can see that mostly Börje is known for this paper, right, Börje? Which was published on cerium as a MOT transition. So you will see that Kalle will talk about something about MOT. And the first talk on this session is about this core level shift, and that you can see already speaker is standing here. He looked very similar to this picture. And that this is the work which we published together with Börje and the experimental group of Professor K.V. Rao. So you can see his picture. And this was when I came first time here, 20 years back. I looked so young. And then Börje is talking about actinides. So I took that picture. I think it was from Vienna, is it? And you can see that this paper is very highly cited. It's cited about more than 900 times in last 8 years. So I will not take much time now. I will go to the first speaker.
Okay, I'm very glad to be here to talk about core level shifts and a few other things. And then first, I would just like to make one comment about this comparison with Nisse Nilsson. Now Börje expects me to pick another person, but that's not the case. It's just that Nisse Nilsson had some sides which I haven't seen with Börje, actually, and that is I'm from the same region and happen to know a guy who played football in Leksand. And then when he was 16 years old, he would play his first game in the football team where Nisse Nilsson also played, Sweden's best hockey player and so on. And then he was very nervous, and then especially nervous playing on the side of Nisse Nilsson. And then one of the first things he managed to do was not to pass the ball to Nisse Nilsson. And then, Nisse Nilsson, this Swedish hero, walks up to him, grabs his jersey, grabs his own jersey, and then says, same color. It was a good start for his football career. I haven't recognized that with Börje, but then, anyway, I should talk about the history of core level shifts, or alternatively, how I got hijacked by Börje. So I was a PhD student in Uppsala, working with photoelectron spectroscopy. And, well, looking especially at core levels, which is a process where you emit a core electron and you analyze that very accurately with an electron spectrometer, and you can determine very many properties of the systems. And the core levels are very nice because they are unique for each element, and it's an atomic process. You get much local information. And of course, my supervisor was Kai Sigbahn in Uppsala. And also looked at valence levels. So we had a project where we were looking at alloys, copper palladium alloys. And in connection to that, as a young PhD student, ended up in Stockholm working with Gunnar Arbman, who had a LMTO code there. And then we actually set off to calculate alloys and simulating disordered alloys with supercell approach, and managed to calculate very large supercells at that time, 16 atoms, or 12 or 16 atoms and so on. There was one publication in the vicinity of that, but that never got published because I was dragged into this smoking cabinet of Börje at the same place because we had saw that these core levels was something that interested us both. And then that was the end of the LMTO career. But anyway, it's and what we looked at was the chemical shifts, which is really the main aspect of photoelectron spectroscopy that made it so useful. And when in the beginning of the 60s, then Kai Sigbahn thought that photoelectron spectroscopy, now everything was measured. They looked at all elements in the periodic table and they measured, and then, what more could you do? And he was actually thinking of closing this activity. And then there were two young students, Stig Hagström, Carl Dodling, tried to measure as much as possible, and then they were measuring everything. And then one weekend, they were running out of samples. So then, what can we find, in the weekend? So they had a key to the photographer. So they got some photographic fixer, and then put it in. And then they saw the chemical shift. And that was really what made this take off, because this is really the essence of photoelectron spectroscopy, I would say, or one of them, which is very important. And this was also the technique for which Kai Sigbahn got the Nobel Prize in 1981. And then accidentally, 1 year after this paper was published then, which was the core level binding energy shifts for the metallic elements. And this was the work that Börje and I was spending much of our time at that time. And looking really at the shifts between the atom, the core level in the atom as you measure it relative to the vacuum level, and for metals as you measure that relative to the Fermi level. And we got really excellent agreement in these cases. It's, if you compare to what was around, it's around, I would say, almost 10 times better. It was really much. And so we sent it to Fischer letters, and then, of course, it was not interesting enough. But anyway, we could make a bit more complete paper and keep the same receipt date and so on. So this was okay. We said that we make it a bit more complete. And then this paper where we looked at all elements in the periodic table, we were extracting this and that and so on. And if you look at this paper, lots of small comments which we put into the paper, like for instance, things that would have been papers by themselves, like this, that it's the surface core level shift is really related or very directly to the surface segregation energy, so forth. We had one thing also was that we really didn't have experimental data to compare with in all cases. We had to derive them, so to say, or yeah. That's a Danish comment. Yes. That's okay. But then, and which means that we had to go through very much of what was around. And there were footnotes where we told why this experiment was not right or what one could extract from it and so on. And some of these, became independent publications. And but it's, anyway, it's a lot of things. So it was slightly larger than the 4 pages that we had originally. And But this was for me, or for us also, generating many other studies. So first of all the metallic elements they were not carefully measured. We could all of a sudden see this. And made this compilation, for instance, together with John Fuggle, which is something that is very much used also, where we had experiments from many labs, but not the least from our lab also. And then we also had a method to derive, sort of experimentally or quasi-experimentally, you could say, with combining data, atomic core level energies for all core levels and all elements. And so we're comparing that to atomic theory and looking at, of course, correlation effects, but also relativistic effects and these things. And one thing that started out as a sort of a failure, we couldn't get this nickel satellite, which was very much discussed in connection with correlated systems, in the right position. But after a while, we got it when we realized how these multiplet effects played a role here. So we had one paper in PRL about that, and this satellite has, well, we continue to work on that lately when in Berlin, where we can reach very high energies also. So we measured the 1s core level satellite on nickel also, which is then at 8 kilo electron volts. And then but what is interesting here is that you have a shell effect in this, which you can understand also where the satellites end up. But I have to confess that for me, the main reason to measure this was that this is the only core level that is named after me. So that's but it's and then to rub it in further, football is important, Börje. So this was World Cup 1986 at Tomatgatan in Uppsala. It's may have looked at Denmark losing against Spain. I don't know, but it's but anyway, you may recognize some people here, and well, you can also, yeah, and then well, working with Börje, you end up with cerium in some way. So I was a postdoc at IBM, working at the Tantalus storage ring in Wisconsin, which was really an excellent synchrotron radiation facility at that time, where I started to work. And the nice thing with synchrotron radiation is that you can tune the photon energy. So, and in connection with the lanthanides, actinides, this was, of course, great, because it was a way to enhance the 4F contributions. And so we did this for the cerium pnictides, and where we could really see two photo emission features, one close to the Fermi level and one a few electron volts down. We also measured for, well, had to do alpha cerium, but we took cerium thorium, because then we could have one sample and then just heat it or cool it and look at the phase transition, and we did this. These were, of course, impossible also to get into Fischer letters, because it relied on some comparisons of spectra at different photon energies, making subtraction, saying that this is 4F. And then the counter argument was that if we do it this way, then we get these double peaks for all cerium systems. And that's, I guess it's exactly the point. But that is, anyway, it's a nice thing. And then at this time, I was with IBM, and well, they were happy for the results, but they complained a lot for the phone bill, which I had with Börje, because Börje was somewhere in Europe, and I was there, and we discussed very much, of course. And coming into this, well, correlated systems can just show that we attended this very interesting conference on valence fluctuations in Bangalore, where high TCs started to come up. And there were, of course, scientific discussions with the cigarette. There were studying papers with a cigarette and not studying physics. with a cigarette. But anyway, this was... so in conclusion here, I would just say that there should be lots of great physics. And then when finally we ended up at the same place in Uppsala, then we stopped to work together on physics, because then it was just politics and so on. But then it was very much at Max Lab, where I was for 13 years, and Börje has always been much involved there, and so forth. And but I would say also it's a lot of great fun working here, and it's more to come. So that's looking forward to this, and with them by saying congratulations and thanks.
So I have to say I feel like a bit of an interloper here, because I've never collaborated with Börje, scientifically that is, and I'm not a theoretician. But we seem to have spent an awful lot of time on parallel committees over the years. So, I guess we've probably been on committees in parallel at Max Lab for 15 or 20 years of various kinds, and then I'd go to ESRF, and I'd find that Börje was there on another committee, and then I'd go to the European Research Council in Brussels and find he was there on another committee, and so it went on. Now, I'd actually quite forgotten, but hearing Ulf this morning reminded me that, of course, I actually evaluated Börje once, because I was a member of a committee that was set up by VR to assess the funding of condensed matter physics in Sweden about 7 or 8 years ago. And I remember that I had the temerity to ask Börje after his presentation. This was all wonderful, but you know, what was he going to do after he retired in about 2 or 3 years' time? Well, I guess we know the answer to that. So anyway, I thought you didn't really want to hear too much about that, but you'd like to hear a little bit of science. And I wanted to talk about core level shifts, because when I thought about it, what I realized was that this key paper that Niels has already talked about with Börje was a paper that helped me a lot to understand about core level shifts back in the 1980s. And so I thought I'd just backtrack to that. So I've given this sort of slightly funny title, which is putting the CA, i.e. the chemical analysis of ESCA, the electron spectroscopy for chemical analysis, into XPS, which of course is X-ray photoelectron spectroscopy. It's the same technique, but XPS is what we tend to call it when we're doing surface science, and I'm a surface scientist, so I call it XPS. So I guess that Niels has already explained basically what the technique is, that you bring in monochromatic soft X-ray photon, you kick out electron from a core level, you look at the kinetic energy, from that you deduce the binding energy, and in conventional XPS, I mean, a lot of XPS is done to determine just the composition of surfaces, and it relies on the fact that the core level binding energy is essentially characteristic of the atomic species. And it's a surface-sensitive technique, because in this energy range, the electrons that come out have a rather short inelastic scattering mean-free path. Of course, we've got this little equation, this energy equation here, and the question is, what is BE? What is the binding energy? And the binding energy, of course, is the thing you measure by this technique, i.e. it's specific to the way you measure it. And that's the interesting bit, because it does vary according to the valence environment of the atom, although it's a core-level species, and the binding energy is largely characteristic of the element. There are small variations depending on the local environment, the local bonding valence environment, and these are the so-called chemical shifts, the core-level shifts that Niels has been talking about. Now, of course, just to go back to ESCA, so this is just a little review from Kai Sigbahn in Phil Tran's Roy Sock in 1970. It's actually just a little review of the books that have been published some years before. And of course, it's stressing this chemical shift. The Ca is all about chemical state identification as opposed to simply elemental identification. And it was very much about spectral fingerprinting, to use XPS or ESCA as a spectral fingerprint of elements in specific chemical environments. And indeed, if you look at a lot of XPS literature, particularly from people doing surface analysis, you see these chemical shifts. So here, I don't know which button to press to get in. Oh, yeah, okay. So this, for instance, is the titanium 2p spectrum from some titanium suboxide. And you see there's so you'd just expect to double it, but you see there's a whole series of peaks, and it's basically, the labeling you notice is just Ti4 plus Ti3 plus Ti2 plus. It's a labeling that sort of implies that the dominant reason for these shifts is the initial state, the ground state binding energy, the one electron binding energy of these states. And that I just show on the right some slightly more recent data, which is actually from a vanadium titanium oxide. And you see exactly the same thing in the vanadium. You see these multiple states, which you can put these simple labels on. But it's really not the whole story. But the idea that this initial state, this ground state, one electron binding energy, is the dominant source of the core level shift actually works quite well in some systems. So here's a compilation from Dave Shirley's group back in 1973 of the carbon 1s binding energy measured in this way for a whole series of different gas phase molecules, carbon-containing molecules, and you see there's a very nice straight line between the calculated energies and the experimental energies, although you also notice there's a shift in the 2 of 15 electron volts, and that shift is due to this final state relaxation, the response of the electronic environment to the creation of the core hole. But in these systems at least, that final state relaxation appears to be much the same for all these different molecules. This is not, however, invariably true, and in the case of, for instance, adsorbates on metals, we certainly expect that to be rather different. And this is just a model calculation from Williams and Lang at IBM back in 1977, and it just shows, it's a calculation for these atoms, oxygen, sodium, silicon, and chlorine, on a gellium surface. So it's a rather idealized calculation. Gellium with an electron density corresponding to aluminium. And it shows the components of this shift, this chemical shift, this core level shift that arise from the initial state, and that's labeled here rather confusingly chemical shift, but it's just the initial state effect. It's the change in the one electron binding energy. And this is the final state, in other words, the relaxation. You can see that, well, as you might expect, that the chemical shift, for instance, is opposite for electronegative oxygen and for electropositive sodium, but you've got this large effect in the final state, and that varies from these different atoms. And when you add them together, you're going to get a shift, which, of course, you can't separate experimentally. I'm an experimentalist, so I want to separate these things. Okay, so then the kind of early attempt to start to put some sense into all this is the paper that Niels has already talked about. So this is a landmark paper, and it puts together a few ideas, brings them all together, and rather spectacularly actually, predicts these core level binding energy shifts for all the metallic elements. It sort of goes right across the periodic table. It's certainly not, wouldn't have fitted into PRL in that form, I think. And the key assumption is basically that the final state, that is the core ionized state, that you assume you've got complete screening in the metal, and so you can basically represent what happens in terms of the valence electrons by this Z+1 approximation, by saying that removing a screening electron near the core, and hence increasing the nuclear charge effectively to the outer electrons is equivalent to just putting an extra proton in the core. And then by a rather neat trick using this Born-Haber cycle, you can relate these core level shifts, the shift between the atom in the free atom and the atom in the metal, to just the cohesive energy of these two elements, the Z and the Z plus 1, and the solution energy of the Z plus 1 in the Z. So the thing that actually we were working on at the time when I read this paper and realized it sort of put some sort of nice, simple physical ideas into this, was actually looking at a quite different problem, which was looking at iodine on little, and looking at the iodine at 4D core level shifts, which, as you see, change with coverage. It turns out that actually interpreting this is much messier than the system that is in the Johansen-Martensen paper, because unfortunately, of course, the iodine is not in a fully neutral state on the surface. It's partly ionized, and so there are Coulombic interactions between them in the initial state, and there are also Coulombic interactions in the final state, and then how fully relaxed the final state becomes important, and it all gets very messy. So in truth, we read the paper, we learned a lot, but ultimately we didn't understand our data, so I'm sorry about that. Okay, this is actually also a nice follow-up to something that Niels was talking about, because the basic idea of this paper, which is, you see, actually 13 years later than this 1980 paper, is actually following up something that Niels picked out in the text of the original manuscript. And it's looking at this so-called surface core level shift, that is, the difference in the photoelectron binding energy for an atom in the bulk of its own solid and at the surface of its own solid. And the schematic is very pretty, because here you see, here's the initial state, the ground state, the solid. Here's the final state for the surface atom. So we've now got a core ionized atom here. So this is what I measure in the photoemission from this state, the difference between the initial state and the final state. Here it is in the bulk. And so, of course, the surface core level shift is just the difference between these two, and the difference between those two is just the segregation energy, the energy of segregation of the Z plus 1 atom to the surface, because the final state we can represent in the fully screened state as a Z plus 1 atom. So it's a nice illustration of the effect. And then I just illustrate that Boyer continued to be involved in this sort of work. So this is now 2005. This is applied to alloys using a random phase approximation. Okay, so then finally I just want to say why this problem continues to interest me and actually come back to the title, which is that if I now try and do some surface science, and this is actually an example of some data from Jesper Andersen in 2003, although I could have showed you some data that's very much earlier from Niels Martensen on platinum. This is on rhodium. And what we're looking at here is the carbon 1s photo emission from CO adsorbed on the rhodium surface at different coverages. So this is at low coverage, and then we go to high coverage, and two peaks appear. And actually, if you co-adsorb with oxygen or with potassium, you see peaks at the same energies. And the interpretation, the conventional interpretation, is really what shows up on here, that the CO initially adsorbs at low coverage in an top site on a rhodium surface atom, and that gives you this peak. And then at higher coverage, you start to fill in hollow sites, and you get this peak. And so this appears to provide a spectral fingerprint of the local geometry, which is of interest to me because my main interest is in surface structure determination. What surprises me is that actually putting co-adsorbed oxygen or putting co-adsorbed potassium on that surface does not change those peak positions, because I would have thought that this highly electronegative, this highly electropositive co-adsorbate would affect the final state and the initial state in the system. But of course, this is still spectral fingerprinting. And the nice thing which has happened just in the last few years is that using modern DFT methods and actually using pseudopotentials from a core ionized state to represent the final state, that one can measure, one can calculate these core level shifts in these different geometries. So the thing you determine is not actually the binding energy, but the difference of those quantities you measure in DFT is the core level shift. And so here in this paper of Jesper Andersen's, they have actually done this, and you see that they've played around with with a couple of different standard codes, here DFT codes, but you get calculated values for the difference that you expect for these two states, which do correspond pretty well to the experimental values. And indeed, this sort of same business has been applied also by Boyer only last year to look at this problem of the germanium surface, where you have lots of different germanium atoms in this reconstructed surface, and to try and unscramble the germanium spectra in terms of these different components by calculating the different core level shifts. And so finally, I just want to show one result from our own work recently, where I have a student who's been doing some DFT. And we've actually been we've been doing some detailed structural work of this furan decomposition on palladium-111, where the conventional wisdom is that you certainly see a co-adsorbed CO and that you produce a C3H3 species. And we've been trying to figure out what on earth this C3H3 species is. So you can do DFT and find all sorts of different conformations with different relative energies. But one of the things, of course, is that you've got 3 different carbon atoms in here, and you can calculate what the core level shifts for those should be, and at least see how they correlate with what you see in the spectrum. And what you see in the experimental spectrum is just a slightly broad peak, but that tells you the shift can't be bigger than a certain amount and can't be less than a certain amount. And it actually allows us to eliminate some of these models, 2 of these models in particular, one which shows no shift and one which shows far too big a shift. So I think these modern DFT methods are actually a huge help, and they are putting on a quantitative basis the interpretation of these core level shifts in adsorbate systems on surfaces. Okay, so thank you, and thank you, Birgit. Thank you.
The half days. But anyhow, I will try to do this, and let's jump right away into the 18th century. Now, in the 18th century, magnetism was still pure occultism. The main person for this kind of obscurantism, that was Anton Franz Mesmer, by the way, a fellow Viennese, and his theory of animal magnetism influenced Europe very, very much. It was only around the French Revolution that finally chemistry and physics became sciences. And in fact, the first scientific experiments in magnetism started around 1825, and being at that time called as experimental philosophy. Let me show you a few experiments, very famous experiments. This is the very first high-temperature study of magnetism. It was performed by Michael Faraday in 1845. You can imagine how primitive his means of experimental research were, but he found out that it appears that only iron, nickel, and cobalt are magnetic, or can be made magnetic amongst metals, and that this is only a difference of temperature, which distinguishes these 3 from the rest, just as it also, in a similar respect, distinguishes them from each other. So in 1845, he had already a very good idea about the temperature dependence of magnetism. And by the way, I mean, 50 years later, this was called the Curie point. His most important discovery was, of course, electromagnetic induction. Now, here's an ingenious experiment by Michael Faraday. It is a rotating metal disc. Underneath, there's a horseshoe magnet. And what he actually could do is to map out the directions of the induced current. Now, the text to the right are always the original quotations, the citations. And this, by the way, is from a letter to Gay-Lussac. It was an open letter. It was 1840. Electromagnetic induction was discovered independently a little later by Joseph Henry. Now, Joseph Henry had a little bit more primitive ideas about experimenting, and what he did to check whether he had an induced current was to have a handle and to feel the shock whether one could see there was an induced current. One could even use the tongue, as he says in his paper. These are the two gentlemen I was talking about, Michael Faraday and Joseph Henry. Now, the most beautiful experiment of Michael Faraday is the following one. It's the lines of magnetic force. You all have seen this kind of figures, and they were first found by Faraday around 1850, and this is from a very famous paper by him. And you know, the experiment is primitive, if you want to. It is a magnet, it's a piece of soft iron, a sheet of paper, and iron fillings. And he found out the field lines of the magnetic field. Now, these field lines, together what I showed you before, the lines of the current, gave rise to a very famous theory. That's the Maxwell theory. And if you look closely, Maxwell in his very first paper used the phrase of Faraday. It's the physical lines of force. That was the expression that Michael Faraday coined. And if you write down the Maxwell-Faraday equation of induction as the following form here, you have to realize that this was not what people were talking at that time. The concept of vectors was still discussed, and the concept of a vector product sounded obscure. So one has to appreciate that Maxwell did something really miraculous. Now, by the end of the century, 19th century, many people thought that physics was out. It's gone. It's over. Mechanics was known, Newton. Astronomy was very well known. It was Laplace. So electromagnetism, thermodynamics was very well known by that. And even hydrodynamics was settled down. And everything had to be solved in the spirit of French mathematics. And French mathematics, that is Lagrange, Laplace, Legendre, Poisson, and so forth. Well, there was one missing link, came in later, and that is the Landau-Lifshitz-Gilbert equation, the Landau-Lifshitz equation, rather, and that was the link of magnetism to thermodynamics. It was only much later, in 1935, that this equation came up, and as you can see, it relates the time evolution of the magnetization to the Helmholtz internal energy. So this is the relation to thermodynamics. Here you have the two guys, Landau and Lifshitz. You saw pictures of Landau. Perhaps you never saw a photograph of Lifshitz. It's well known, once the new century started, new difficulties arose. And it was the, so to say, the obscure feeling that one could not interpret line spectra. As you all know very well, Bohr was the first one with a kind of zero level of quantum theory in 1913. But before him, there was something else. And you have to appreciate this. Although Maxwell had already connected the light with electric field, it was now something completely different. Namely, Albert Einstein published a mass-light relation. And that was very, very important. It was linking the concept of mass to light. And this equation here really changed physics and, of course, puzzled many. You all know this. Louis de Broglie became famous because he was fiddling around with Einstein's equation and with the equation energy equals E nu. And by using a kind of bad mathematics, he came up with a beautiful result relating the relativity to the Bohr model. Now you have to realize that this was the real starting point, because Schrödinger was so much influenced by de Broglie, and this is a quotation from Schrödinger's first paper, and he says, that the incentive for his paper was the ingenious ideas of Louis de Broglie. But Schrödinger also said, that it's not complete. I couldn't include relativity. At the same time, it's only 4 years that separated everything here. There was another experiment, and that added a lot of confusion to the public and made magnetism even less easy to understand. Now, here's a quotation from Max Born to Albert Einstein, saying, although he was a theoretician, he constantly hung around with experimentalists. Now, guess who this was? This was Otto Stern. And you all know the famous Otto Stern-Gerlach experiment was more or less the discovery of the spin. Now, there we had a new concept and new confusions. And it took about 4 or 5 years till this confusion was settled by 2 guys, namely Wolfgang Pauli and Paul Dirac, more or less at the same time. To the right, you see the original paper or the headline of Paul Dirac's paper in the Proceedings of the Royal Society. And as you can see, I put 2 very strange symbols there, namely a sphere and a Möbius strip. And that is to indicate that the world of Schrödinger are functions belonging topologically to a 2-sided surface. It's a 2-pi world, whereas the world of Pauli and Dirac are functions belonging to a topologically 1-sided surface. It's a 4-pi world. Now, if you want, this is the conceptual level at which we have to talk about, or we should talk about magnetism now. I put there time-independent magnetism, right? Because what is still missing is to put in the concept of time. Now, how do we do this? Right? Is one solution using a time-dependent Dirac equation in the presence of an external electromagnetic field? We don't know how to deal with that. We have other means. I haven't even seen a Pauli-Schrödinger equation time-dependent. So this is our present terra incognita. So we are not finished with magnetism. But at least 2 very famous experiments in the literature could be explained. And I want you to guess the name of the following famous effect. This is the original paper here. Just to read a few lines. Between the poles of an electromagnet, the middle part of the flame from a Bunsen burner was placed. A piece of asbestos impregnated with common salt was put in the flame in such a manner that the 2D, you can read it better than I from this angle here. Anyhow, so if the current was put on, the 2D lines were distinctly widened. If the current was cut off, they returned to their original position. Now, the author of this paper was very humble because he said at the end, possibly the observed phenomenon will be regarded as nothing of any consequence. If you haven't guessed it, this is the Simon effect, right? And what he saw, of course, is the broadening because the resolution of his spectrometer was not good enough. He only saw a broadening, and of course, we all know this is the famous Simon effect, and it is from 1897. I have still another test. Here's your equipment. 1 light source, 2 nickels, 1 horseshoe magnet. Okay? And we have to discover what is the physics with all this, right? We have no idea. So in case you don't know what a Nichols prism is, it's down here. It splits an incoming light ray into an ordinary ray and a ray of plane polarized light. and we shine in the plane polarized light onto the north pole of the horseshoe magnet. Okay, so let's do the experiment together. So we twiddle around with the left nickel, and bad luck, nothing happens. Absolutely nothing happens. However, if we leave the left nickels, switch on the current or the magnetic field, and turn the right nickel, suddenly there comes a ray out of the nickel. Bingo, we found another effect. Big question, which one was this? Which famous effect? Well, that was the Kerr effect. And what it does, linear polarized light in magnetic ambiente becomes elliptically polarized light, right? So this is the famous Kerr effect, which it just discovered by two nickels, a horseshoe magnet, and a lamp. I put down in the last line, bump probe, femtosecond magnetism. That is why we need the concept of time, right? The new experimental data are on the scale of nano, femto, picoseconds, and perhaps in future attoseconds. So this is what we miss altogether in magnetism still. Well, Kerr, I wish you all the best for your birthday, or as we say, up to 120. And by the way, since we met in Los Alamos about, I don't know how many years ago, in 1985, I put down as a kind of a reminder a cocoa belly. And for the first time, it's a premiere. The cocoa belly is producing Scandinavian music. So, thank you.
Give you a little bit of history, and then take you all the way up to some modern things that have us excited right now. Okay, I want to start with the first time that I know that punch cards were used in the electronic structure calculations. This is a computer, John Vincent Atanasov, a Bulgarian heritage, got his undergraduate degree at Florida University of Gainesville. And then he came to Ames, was a professor for a while, a master's degree, and then went to Wisconsin with John Van Vleck, where he picked up this thing called quantum mechanics. And his thesis, 1928-29, was on the electronic polarizability of a helium atom. And it was published in Physical Review in 1930. He came back to Iowa State, and then his graduate students were stuck because they had to now skip helium and go to lithium and beryllium and so on. And the calculations, because you're using quantum mechanics, get pretty difficult. What they had available was essentially what Hartree had. Well, Hartree had his father with the clickety-clack mechanical calculators. And Atanasov said there has to be another way. And so he developed the electronic digital computer. Vacuum tubes were the processing units. There weren't transistors back then. He had electrostatic drums where he could memory, little tiny spots on that he could charge. And here's the card readers here. And that was the basic input-output for that machine. And it worked, but unfortunately it worked pretty well. There were people, one of his students, Clifford Berry, was using it. But then it had, the card reader was the fault. After about 150,000 punches, something went wrong. I mean, it wasn't so reliable. He went off to the war effort, and he did file a patent with the university, and the university neglected to file the patent. It was only in 1973 that the world really became aware of it, because Sperry Rand had picked up the patent from ENIAC, and was charging people a lot of money. And then they heard that Mauchly, one of the developers of the ENIAC, had visited at the Nassau and picked up quite a few ideas. He spent a week taking notes. And in 1973, the patent on the computer was thrown out. And so the judge decided this was the invention of the computer as far as legal concerns go. There are other people that have contributed, certainly, to the computer. Okay, anyway, I wanted to start with punch cards and electronic structure calculations. You're always in danger with computers and trying to make predictions. Watson, chairman of IBM, I think there's a world market for maybe 5 computers. 1949, Popular Mechanics, computers in the future may weigh no more than 1.5 tons. I've traveled the length and breadth of this country and talked with the best people. I can assure you that data processing is a fad that won't last out the year. The editor of the business books for Prentice Hall. This one I like a lot. There's no reason anyone would want a computer in their home. Ken Olson, chairman of Digital Equipment Corp. 1977. But the one I like the best is this one. 640K ought to be enough for anybody. So things are changing. Now let me go back to my favorite element, gadolinium. This was discovered in the Ytterby mine, not very far from here. A few years ago, Gordon Grimwald and I left a big sign, hand-painted sign in the mine area, next to a tree, for the Rare Earth Conference, which visited 2 months later. And the sign was found its way back to Ames, Iowa, on Carl Schneider's desk. This is a nice element and one that was first calculated with, there's the spaghetti, by Dimick and Freeman, 1964, part of Slater's group at MIT. And it was a surprise to people that all of a sudden D-bands showed up and it looked like a transition metal. But people were interested in magnetism. This was a real Herculean task at that time. And you have to worry about all the different electronic structures of the orbitals. The 4Fs are deeply buried inside. And it became my thesis. Art Freeman went to Northwestern, and I was a graduate student just starting when he arrived. And my thesis then became gadolinium, but spin polarized. And what we looked at, I looked at the form factor, calculated the spin density and the Fourier transform of that, because it was just being measured by Ralph Moon, Kohler, Cable, and Child. And it showed, one is that our calculations are non-relativistic. We're not in line with the neutron magnetic form factor. And then the conduction bands are showing up here. And that was a motivation for us to try to put relativity in. And Dale Coling and I, 1977, published a spin polarized, what's now called the scalar relativistic method, to include relativity into these calculations. That was interesting because in 1976, when we were working on this, Dale went to work with Gunnar Ardman and Borja at FOA in Stockholm. And I was working in Riso in Denmark and spent the summer there. And then I spent a week with my wife visiting Dale, Maria, and Borja and Gunnar. But actually, Borja wasn't there. We took his apartment. And I will tell you that his apartment back then did not look like the one he presently is residing in. It was, my wife and I still have very distinct memories of the features of that apartment.
Tell us.
No, that's... some things are better left said. Okay. Punch cards. That, by the way, my thesis was essentially punch cards and trays, and you had to really sequence those cards, or you could be in trouble when they dropped down the stairs. It only happened once, and then I remember. Research moved on to D. Haas van Alphen and gadolinium, optical properties. This was something fairly recent on that we developed X-ray magnetic circular dichroism, and I did it for rare earths with Paulo Cara in Grenoble. They were just building the synchrotron there, and I was working there while the synchrotron was under construction. And Jerry Lander now lives near a house where I was living, I guess. So it's a small world. This is just density functional calculations here of the gadolinium L3 edge. And you can see as the temperature is lowered, the experiment starts to pick up and goes right to where the theory is, the dash curve. We could also look at the germanium K edge, and again, with temperature dependence, it fell right into place. So this was a FISREV letter when we did this not too long ago. This is another example, contains gadolinium. This is a magnetocaloric, and it could be used in engines and material. Gadolinium-5, silicon-2, germanium-2. They're getting more complicated. The details of the electronic structure and total energies and the phase transitions that take place in this material require quite a bit more computing power. But of course, that's the wonderful thing in our field. If you can't do it now, a couple years from now, it becomes feasible. And actually, another few years after that, it becomes, I wouldn't say trivial, but it's well under control. This is one more recent. This is just recent. It's not on gadolinium. This is a iron arsenic material, calcium iron 2 arsenic 2, where we're the experimentalists. This is where we're starting to really the theorists had been in a position of needing the experimentalists to give them some tidbits of work and what's going on. Right now, this is partnership, complete partnership between theory and experiment. One of my students right now who's just finishing up, Steve Hahn, they don't do an experiment at Argonne using the inelastic X-ray scattering there without him coming along. He can calculate the structure factor on the fly for them. So he has to stay up all night drinking coffee and talking physics with these guys. The spectrometer is one where you take 20,000 electron volt photons, hit the crystal, and you have to resolve 2 millielectron volts. Think about 20,000 electron volts resolve the energy difference of that scattered. And the arm on that spectrometer is about 9 meters long. It's a very big, monstrous thing. Here you can see the non-magnetic calculations at room temperature don't quite agree. The experiment are the white dots. The theory are the red. He's just plotting intensity here from the calculations. If he does it with the magnetism, you get the splitting and, in fact, a much better agreement. So it means that the magnetism is still present even above the Néel point where you get paramagnetism. The magnetic influence on the iron is still present and influencing the phonons. Okay. Now, we did in Iowa State worry about making square cows so we could ship them better. And we brought in a consultant. This is Borja, showing how to handle the cow. This is Carl, Mr. Rare Earth, and this was one of the times you visited Ames, and we had good discussions on various things. But
if you go back and point out the brownie, the cookie.
Oh, all the way back, he was looking. This is a cookie, okay. This is now taking you to the modern era where we're operating now. This is just showing the slide that you've probably all seen, the increase in gigaflops of computers. This is stopping here, but it's going up to about 6 to 20 petaflops if you want to keep going right now. So the computers are different. Whoop, go the other way. And this is a roadmap that comes from the Department of Energy right now, where they see things going up to 2018. And so we're maybe we didn't hit 20 petaflops in 2011, but it's pretty close, and we're over petaflops now. Not quite up to 20 in the United States, but I think China is up there, or Japan. But what's the key problem? Of course, you're having more processors. The system side nodes is projected to keep growing. When you're at 100,000 AMD processors at Oak Ridge, you're getting 32 GPU units from NVIDIA on each of those. Whether you can make use of them and how to make use of them, it's a challenge for the young programmers and the young people going after it. Of course, once they do it, they become very valuable commodities and can go where they want. Power is the big thing. You're going from 6 megawatts right now, and you want to have a factor of 500 to get to the exaflops here and only increase the power by a factor of 3. It seems impossible, and that yet has to be done. And that's where the Intels and the other people are pushing the effort, the NVIDIA chips and others that use less power. So we'll see what happens on that. But I wanted to give you leave you with just one example of where we're trying to use that kind of power. A genetic algorithm structure search for iron cobalt alloys. This is not particularly great importance. It's an example to prove that we can scale the machine and get extra time, because we want to look at, for hard materials, not containing rare earths. Rare earths are too expensive, and China won't let you have any anyway. So the demand for rare earths is huge, and some of the places in the United States are funding us to look for, not just the theory experiment together, to look for beyond rare earth hard magnets. But how do you do the phase diagrams of ternaries and quaternary? How would you ever have gotten neodymium-2 iron-14 boron, 68 atoms per unit cell? Well, right now, with the way we're doing it, we think there's a good chance we would be able to find such a thing. What this is, those are my collaborators, by the way, Kai Ming and who just won the Anis Rahman Award from the APS in computational physics this year. This is we're essentially taking a box and putting atoms in and finding the ground state energies. And here's the different configurations for different thousands out of thousands. And you can see there's a couple configurations of those atoms. This has only got 16 atoms in the unit cell. We're up to 50 atoms in the unit cell. We're getting more time on the computers. And you're talking millions of node hours. And right now, we're scaling linearly. As you increase the number of nodes, we get a linear scaling with the output over 100,000 processors. They won't let you have the machine this next year unless you can scale up to about 80,000 to 100,000 processors. So we're looking for lower energies. Not that we're going to trust the theorists too much. We're going to find the sweet spots in configuration space. There are ways the experimentalists are doing that too. And we're trying to work together to locate and isolate the places where we think the best candidates are. So there's hope. At least we have to write that in the reports. And it's really an exciting adventure right now. If this is opening up theory leading experiment, or at least partnering with them in a more critical way. Okay, conclusion, petascale computing will greatly enhance theoretical capability to search for new critical material candidates, and strong partnering with synthesis and characterization groups promises to greatly accelerate the discovery of new materials. And finally, it feels like we're just getting started with whole new things going on. So come on, Bori, let's keep it going. And many thanks to all our colleagues in this wonderful field. Thank you.
Okay, so I will talk about the graphene, but before that, I need to find the motivation. So that's, 2 years ago, that's my first time to visit Sweden, and Boyer is very nice to show me the Royal Swedish Academy of Science, where he worked. So you may see the Boyer who opened the door for me. And the next slides, we are sitting together to take a photo together, and the sculpture of the Nobel. And at this time, this chair is empty. So Boyer is not the chairman yet, but so he sits over there, but he becomes the chairman very soon. I don't know which year. Forget. But not the 2010. Not at least not August. Anyway, but at that time, Boyer told me some story, older story about Waller who was doing some homework in Uppsala library. So the other guy check what Waller read, so they can guess the Nobel Prize. But nowadays it's hard to do so because you have to hack into Boyer's computer to do that. Yeah. Actually, I have a student who help you doing something, so she may have that opportunity. Anyway, so at that time, we don't know that what they decide. But after 2 months, okay, it is announced that the Nobel Prize go to graphene. So I suppose Boyer voted yes to that, right? Okay, so today I will talk about our research on graphene. Actually, some of the research are motivated by the Nobel Prize, so it shows the importance. So in the last about 3 years, we have done some calculation on the Kerr's mechanism and also the band gap engineering mechanical property on the pristine graphene or chemically modified graphene, as well as the graphene oxide, which we have proposed some structural model, some chemical modification, and it can be used for gas absorption, separation, and also with metal decoration used as a catalyst. Of course, I don't have time to speak all of them, so let's go to some more physical part. So today I will concentrate on this mechanical property like the boundary effect and the effect of oxidation. So my first topic will be the boundary effect on the strength of graphene. So why graphene is so important? One reason is that it is the strongest material ever being measured. So this is an experiment in 2008. It was reported that the Young's modulus is as high as 1 gigapascal, and the intrinsic strength, which normally we calculate but cannot measure it directly, it is as high as 130, which agree excellent with ab initio calculation. So this is a system which means very important in as an ultra-strong material. So, however, in real graphene sample, normally you can grow polycrystalline graphene. So there are always some green boundaries between the single crystalline domains. So what will be the effect of this green boundary on their excellent mechanical properties? 2 years ago, there have been a science paper report that for some selected symmetric green boundaries, the intrinsic strength can be very high, almost as high as the pristine graphene. So it's up to 100 gigapascal. So the question is, how about the others? Because as we can see that there are so many kinds of green boundary, almost infinite possibilities. So what will be the systematic trend in addition to these selected symmetric boundaries? So we have done some more systematic work, and we built a structural model, and we consider up to 20 green boundary of different kind of possibilities. And first, we look at the formation energy and as a function of misorientation angle and inflection angle. Well, can I have this pointer somewhere here? Okay. Okay, yeah. So here is the inflection, so you can see the barking here. Basically, the formation energy doesn't show much dependence on the inflection angle. Well, it has some relationship which has been already proposed with a misorientation angle. So more importantly, we check the intrinsic strength, which you can determine from this dropping point of the stress strain curve. And then you can extrapolate this intrinsic strength, and then you get this as a function of inflection angle. That's the plot we get. By extrapolating these things to zero, we can have a linear fit of this relation. So this means that with inflection due to the existence of green boundary, the intrinsic strength drop significantly, and it drop almost linearly. And the tau zero is the upper limit, which is actually calculated for zigzag graphene, is about 100. So for those without inflection, they still have some trend that, as we can see, that for the zero inflection, there are some symmetric green boundaries. The intrinsic strength also changes with formation energy. So it ranges between 70 and 100. So basically, we have some systematic trend which might be useful to guide future experiments. And we further examine how do this system fluctuate and sufficiently large tensile strength. So we run MD simulation, but not ab initio, this empirical MD simulation. Interestingly, we find that the initial fracture may happen either on the boundary or inside the domain, which is unexpected indeed. And the fracture initiates from either breaking of the bonds or a Stone-Wells transformation. So this is the first part of my talk. And the second part is the mechanical property of graphene oxide. Graphene oxide is a counterpart of pristine graphene and can be very easily made by oxidation of graphite. And also, it is a very cheaper way to achieve graphene-related materials. The mechanical property of graphene oxide has been measured. There's 2 experiments, and it was found that the Young's modulus and the elastic constant are lower than pristine graphene. In our previous work, we have proposed some structural model, in particular, this structural motif for graphene oxide. And then we can assemble this zero-dimensional localized motif into some ordered structure or disordered structure into 2-dimensional periodic boundary condition. So we propose 2 kinds of structural model for graphene oxide. Then we use this ordered or amorphous structure model to study the mechanical property of graphene oxide. So we have put either ordered or random distribution of the hydroxyl and epoxide groups on this graphene, and then we study the effect of coverage, or we can say oxidation rate. So what we get is we find the Young's modulus drops, but rather slowly with increasing oxidation rate. And we can find that the number we get here is actually agree very well with experimental measurement. Is about 250 or something around. That's the Young's modulus, and also we can reproduce the elastic constant, which is also reduced from pristine graphene. With as you increase the oxidation rate, it drops slowly. So similarly, we examine the intrinsic strength. This is the intrinsic strength for different coverage rate. And if we look at the table, we also find that the intrinsic strength drop with increasing number of oxidation. So basically, that's a major finding. And if we compare the older structure and amorphous structure. In other cases, the older structure are stronger due to the highest thermodynamic stability, either in this Young's modular case and in the intrinsic strength. We further look at the failure behavior. Where did the first bond break? And we find that in the tensile strand, the sp3 carbon-carbon bonds fracture first, because this bond is longer than the other bonds. So here is a brief summary that I think I will just put here, and you can read it. So basically, we can understand the fundamental mechanical property of graphene and its derivatives very well from ab initio calculations. That's all. Thank you for your attention.
When Levente asked me to urgently send the abstract, I had to think about what to do with the title I had submitted a few days before. So I came up with this abstract, so I submitted this as an abstract. I'm not sure if Levente was really happy with it, but I would like to convince you that it really captures all the physics I'm going to talk about. So coming back to the question, what to talk about, so we have a kind of long-standing collaboration. We didn't publish so much together. And I was thinking, what are the common topics we have? And one of these common topics, at least for the last years, is certainly metals and metal alloys. So I remember in 2000, I think it was, when I was here for a year, that you were so enthusiastically talking about ab initio steels. So the first thing it came to my mind was talking about steels. But actually we have seen so many pictures now about Berje with smoking, swimsuits and things like that. Actually I know Berje as a more elegant person, and I thought that talking about steels would not be noble enough. And as I know, Berje is not a committee member of the Ig Nobel Prize, but rather of the Nobel Prize. And actually, I don't know what this material here is, but I thought it would be more appropriate to talk about noble metals. So before talking about noble metals and the results, I would like to point out another thing we have in common with Berje, and this was the Exciting Network. It was an EU research and training network running from 2002 and 2004, where Berje was leading one of the nodes, the Uppsala nodes. It was all about optical spectroscopy or theoretical spectroscopy. So we started with a kickoff meeting in Graz, where some of us probed the excited states already. It went on with a summer school in Riksgränsen here in north of Sweden. We had the midterm review in Aarhus in Denmark. So, and you may guess what all these pictures have in common. We discussed a lot of different physics, but there was one question which was always open, and this was, where is Berje? So actually, if you look, I scanned through all the pictures of this network, and I never could find a picture where Berje is on. Sorry? He was shortly there, yeah? I remember he gave a talk. All right, so let me come back to results, to research. I would like to combine now the spectroscopy with noble metals and talk about optical excitations of metals. Well, before coming to complex alloys and to nanostructures, I think it's crucially important to understand the basic materials. And it's not so easy also to find experimentalists who have the same view on that. But happily or luckily, I find an experimentalist, Wolfgang Werner from the Technical University of Vienna, who also was interested to study very simple materials, simple metals, again, from scratch, because all the experimental data which you find, for instance, in Palik's book, which is considered to be the Bible of optical spectroscopy, they were taken at the end of the 60s or beginning of 70s. So we did the simplest possible thing you can do. We were running DFT calculations for 17 elemental metals. What you see here in all these graphs is a comparison of DFT, this is given in red, with the new data by Wolfgang Werner given in black. And what we will see throughout all these materials, that all the absorption onsets and the structure of the optical spectra agree very well with each other. And they agree much better. You see many discrepancies with this old Palik data, so the new data and the DFT data agree very well. So let's go through this, starting with silver, gold, copper, whatever. So we were calculating quite a few materials, and we find actually all the trends all over the place. Summarizing, there's excellent agreement up to 100 electron volt. The new experimental data agree much better with DFT, but of course, if you look into the details, these details matter. And to this extent, I just pick out one example, and this is silver. I mean, you see from this mess out here how important it is to have reliable data. Otherwise, we cannot really compare our theoretical results and evaluate our theories. If we don't know what the real data are or experimental data are, we don't know how good the theory is. But in any case, even if we're happy now, or much more happy with the new data, which gives us at least the same peaks, the same structure in most of the cases, there's of course room for improvement. So details matter, and in particular here in the absorption onset, and this has simply to do with the fact that DFT doesn't capture the right position of the D-bands. So far so good. We know this, of course, but in general, as we've seen, there's very nice agreement between theory and the experiment, even for properties which DFT is not supposed to give correctly. What does this mean? We can now take our theoretical spectra and look at the colors they're producing. This is a collaboration with Cecile Beer's group, and Audrey's Alkauskas did most of the calculations, and Stefan Sagmeister in my group wrote the DFT code. So let's have a look at what PBE predicts in terms of colors. Okay, copper would be blue, silver would be green, and gold would be brown. Can you imagine a Nobel Prize medal to be brownish or so? It doesn't really nice. So let's do better. Let's go beyond DFT and include the GW band structures. And then you see that everything comes out much more nicely. As mentioned, Stefan, well, is coming from my group. This is an Austrian coin. Cecile Beer is Swiss, and Audius is Lithuanian. So this is a Lithuanian gold coin or whatever. I'm not sure if it's really 100% gold. But what you see here is that now the Nobel medal looks much better. Let's stay for 2 more minutes or so with copper, silver, and gold, the coinage metals, and go to those properties which are supposed to come out nicely from DFT, and which actually my title is about. So let's go to cohesion. How do our favorite functionals perform here? This is a very busy slide. It shows you the cohesive energy of copper, silver, and gold as a function of lattice parameter. And since PBE, for instance, is so well known for producing so nice lattice parameters, we have a look at the PBE results. So these are the curves which are given in black here. In fact, for all the 3 materials, you find that the minimum is very well captured at the experimental lattice parameter. This is true for copper, for silver, and for gold. For the cohesive energy for copper is perfect, just lies on top of experiment. But if you look at the cohesive energies of silver or gold, then you're quite surprised. So the cohesive energy is wrong by 1 electron volt or something like that. So that means that even if you're calculating supercells and nanostructures and whatnot, it seems that we don't even understand or fully understand the most simple materials. So cohesive properties really gives us a headache. We could analyze this by looking at the different contribution for exchange and correlation separately. And what you see here, of course, is the error cancellation effect. For instance, if you count now the error of LDA with respect to exact exchange, it's 2.7 electron volt. If you look at the error in the correlation, it's minus 1.7. So these 2 effects cancel each other. So in general, we know already, but in general, DFT results are not so bad. The error is smaller in PBE. So this is exchange part, this is the correlation part. Of course, we shouldn't compare exchange and correlation separately, but what we can learn from these figures is how important non-local correlations is. And sorry? Yeah, sure. We shouldn't. It's fine. I think it's fine. But as soon or the closer we come to the exact functionals, then we can compare how wrong the approximate functionals are. And even if you shouldn't interpret LDA exchange correlation separately, what we can learn from this is by knowing what exact exchange is and RPA for correlations is, then we see how important non-local correlations is, or van der Waals interactions, if you like. So then we learn that it's 2 electron volts or something like this. But the non-local correlation contributes to the cohesive properties, and this is the reason why our functionals fail so badly to describe the cohesive energies. So far, so good. So far, the understanding of simple materials, but let me come back now to the questions I have been asking before, namely, where is Börje? We never found him in any of these network meetings. I didn't see you for a really long time, for the last years. So actually went back to Uppsala 10 days ago or so to search for you. And I came to the institute. I came to your office. I mean, what you really see here is there's a lot of information about cohesion. So of course, I was reading all the papers to find out what has been published before and whether all this knowledge which we published are already there in Börje's office. But I could look around for hours, and even I spent there 2 days, but I couldn't find him. And so I'm really happy, Börje, that you are here today. And I would really like to thank you for all the support and for the wonderful time I've been spending in Uppsala and also in Stockholm more recently. And I would also like to emphasize that when I came to Sweden the first time, I really thought that Sweden would be paradise scientific. But I very soon found out it's not Sweden which is the scientific paradise, but it was Börje who really made the paradise for the people working with him and around him. And I really would like to thank you for this, and happy birthday.
I was probably the first one among you to collaborate with Börje and also to meet him. And this is very long ago. It's almost ancient time. You complained about the computers, that the memory was too small. Even in the photos, there were too few pixels, so that's why it's a bit shady here. Anyway, what we talked about at that time was Mott, Wigner, Slater, Hubbard, and basically the correlation problem. And these correlation problems come up today as well. It's a very glorious day, Börje, here. There are a lot of people that sort of admire you and talk nicely about you. And I remember when we started, let's go on to the next one. It was in 1966. Many of you were not even born at that time, or if you were born, you could hardly walk, I think.
Now we can't do that.
Yeah. Well, I didn't say that. Anyway, yes, we ended up sort of at the Swedish Institute for National Defense in Stockholm. It's always called national defense, not national aggression or national war, but for some reason we ended up there. You came from Nordita, where you studied with Dick Mattuk, second-order phase transitions, Green's functions, etc. I came from Uppsala, from the quantum chemistry group. I spent some time in Moscow and just returned studying Green's functions. And the atmosphere was very different at that time. I think you and I considered ourselves sort of outcasts in the academic system. We were actually, because we didn't have sort of the protecting godfather who would guide you to positions, etc. But we sort of were ourselves, in a way, we were orphans. And that was a nice time, because no one in principle told us what to do. We didn't listen to the boss, so we did what we wanted to do. That was a nice time, and I guess we had a nice boss or weak boss or whatever, but we carried on the physics we were interested in. We were not interested, we didn't think about actually getting a PhD. We did the physics we did because we thought it was nice. And our offices were like sort of a smoky battlefield. I remember when it came in the morning, we cleaned the big screen and made it very clean, then spent the entire day discussing smoking. So that's why I had this smoky atmosphere. And I'm happy, Börje, that we are still around here. Anyway, that was a very happy time, I think, because we didn't have to spend time on committees. We didn't take courses at that time. Had we had courses to take, we would not have been here, I think. Okay, so the principal problems that we were interested in, opening of energy gaps, metal insulator transitions, basically, and the magnetic properties associated with that. One paper, the oldest one, is of course by Wigner on the Wigner lattice, that an electron gas should become a crystal at very low densities. And it also should become antiferromagnetic at that point. It's been very much looked for so far, not really spotted in a good way, but I think it's sort of will soon be, or is being on that stage right now. Then Slater's work on the magnetic effects on the Hartree-Fock equation, splitting of bands, and the occurrence of magnetic states. I think you formulate it differently today, but this is the basic paper. And they had Neville Mott and his work on the metal insulator transition, and the very famous Mott criterion that the density times the Bohr radius should be around 0.2. So it's a localization that an electron traps. It gets trapped because of correlation or screening. These discussions, I think, became very important because it was a starting point of Börje's work on cerium, where he said that cerium, the F electron, when it localizes, is a Mott transition. And we also did work on the hydrogen somewhat later from Fuba, where you compress gases, hydrogen, to very high densities, and you get the metallization. And this fits rather well with Mott's ideas. You're talking about sort of all nice publications and tremendous citations. I remember we tried to publish this hydrogen paper and got the referee report that it's too simple and one should not believe in the experiments because we had got the perfect match to experiments, but that was not enough. So that remained unpublished or as a report somewhere. Anyway, I looked at it recently, Börje, and I thought it was very nice work, actually. Very clever, very simple. And of course, we didn't have computers, really, so that's why we smoked and talked. Okay, Hubbard was around in the electron correlation in narrow energy bands, and similar states are Overhauser spin density wave states and Levdine's alternate molecular orbitals, which is another way of actually writing Slater's theory. I said that we were sort of keen on Green's functions, and this was kind of fashionable at that time, so that's why I'm showing these diagrams. We formulated the alternate molecular orbitals, so the Slater split band model, in terms of Green's function and symmetry breaking. And this is more or less a mapping from the BCS theory. It looks very similar. You get a gap equation, you get a critical temperature, etc. So we were very pleased with these Green's functions, where you have a normal and anomalous Green's functions. And I think we were more sort of interested in the aesthetics of this. And we did a little calculation on the free electron gas with delta function interactions. And at least we see here at low densities, at large RS values, the antiferromagnetic state becomes more stable. So this would be sort of a switch over to spin density wave state or Wigner lattice. We thought at that time it was very, very, very artificial. Today you could talk about the electron gas in a heterostructure, in semiconductor heterostructure, where actually this delta interaction is a rather good model. You can replace Coulomb interactions by delta interactions in quite a reliable way. Okay, we did a 1D chain where we applied all these grand Green's functions and did some calculations, but it's really 1D chain with a cosine dispersion, and found that you get a band splitting, you get a band gap opening up, and it actually is open all the time, independent on the hopping integral here. So it's always an insulating state, and I remember we wrote in the article that it's a clear bearing on the Mott transition.
Did you really use the address fuck Stockholm?
I'm going to tell you another thing. I remember that this was the first paper that was ever published from FOA, the National Institute of National Defense, that was published in Physical Review. And we stormed into the office of our boss and said, "Hello, see what we have here." Oh, he said, "Oh, that will cost money." Do you remember that? Okay, we went on to even more fancy diagrams. Here is the Dyson equation for finding the collective mode in this 1D chain. And actually, we did solve this numerically, and I think Börje showed actually great skill in writing up these equations and showing how to solve them. But again, I remember you had a big sort of picture or poster or whatever where you had these diagrams, and you had painted them in blue and red and green. You still have it, yes. It's very nice looking. People don't do this any day, these days, but anyway. And I also remember from this 1D chain, which is really big, long carbon chain, and we were actually onto some planar molecules as well, carbon molecules, that our sort of wiser colleagues remarked that it was completely artificial. Why should you do that? It's just a mathematical exercise. And I guess we're both pleased to see all the 1D systems being fabricated and studied today, so blame on them. And we also carried on with this Slater split band model, and we formulated or did a paper. We had a fellowship to the Free University in Brussels. I remember we worked at nights for some reason. You could work there until 2 o'clock, 1 or 2 o'clock in the morning, and then go out for dinner as the restaurants were open. So we enjoyed the time very much. And this is a paper where we put impurities into the split band model. And again, you could more or less follow the BCS theory, more or less map it over. And we're very pleased or proud of the title here. It's the best title we ever had, I think. Dirt in Slater's split band model is kind of not completely clear what we mean here. But anyway, we didn't get this paper published in a very good journal. It was sent to Physical Status Solid at that time, where they had didn't have any peer review, so it was accepted. I looked at the paper the other day, and I think it's still very nice. It's a good paper. Okay, to make a quick jump here to modern time. If you look at the Wigner lattice, which is an electron gas now at very low densities. And because of correlations, electrons want to order themselves and make a regular lattice. It has been looked for ever since Wigner invented or calculated or suggested this type of lattice. And as far as I know, it has not been found until very recently, where you have very strong indications that it is around. Does this one work? Or? Yeah, okay. So suppose you have a 2D electron gas, which you can fabricate it with a semiconductor heterostructure. You layer gallium arsenide, aluminum gallium arsenide, and with aluminum arsenide, and you dope it, and you etch it, and you do all kinds of things. Then you can create a channel here, or a wire, quantum point contact, or a wire. If it's long, it's a wire. If it's very short, it's a quantum point contact. But anyway, when you measure the conductance as a function of electron density, when you change the width of this channel here, you get conductance steps, which are 2e squared over h. It's very fundamental. A bit similar, actually, to the quantum Hall in terms of fundamental constants. And typically, what happens when you change the width here, that you have transverse waves, transverse states across here. And when they become occupied, you open more and more channels. So the wave function would look like this. If you have 3 channels open, you have well, 3 levels occupied anyway. So then you would come up to this plateau here. This is a simple theory. It's a simple experimental results. So far, they're very famous, these steps. And very recently, there was an experiment reported in PRL on where the substrate is not semiconductor, but it's actually helium, and you put electrons on top of that, and you form a quantum point contact. And then you find that these electrons in the point contact order, they make a Wigner lattice. That's fine. The drawback is that the temperature is high. Density is very low, so you don't need much of a temperature to make it high. So these are classical electrons. So it's really plasma that localizes and becomes a crystal. More recently, you find that these conductance plateaus collapses in a way that indicate that you get the formation of several bands, and you get the formation of a lattice. So the 2e squared over h gets disrupted, and you form a lattice instead. And I should end here by showing a graph, which I'm sort of pleased with. This is the spin polarized DFT calculation of the electron gas in a wire, that circular wire, or cylindrical wire, sorry. No, circular wire it is. And you can see here, this is a spin-up density, these blue sides here. So evidently you form some kind of a zigzag lattice when electron density becomes very small. And in the same way, you get also spin-down lattice, which is not shown here, but it would be the same, but shifted in phase. And when you put them together, you form a lattice, very clear lattice here, would be an antiferromagnetic Wigner lattice in a 2D electron gas at the interface of a semiconductor device. So a lot of things here are happening, and what sort of the kind of simple systems that we talked about, where they are still alive, and they're actually also becoming very realistic. There are a lot of measurements, and I think we will see a lot of this. So I will stop here and congratulate you, Börje, and also thank you for the time that we worked together at FOA, because that was a great time.